Chapter 10, slides 14 to 21. Okay, so remember I said that I wasn't giving you protic solvents in those previous cases. Well, we're going to learn why I was keeping it really simple when adding HBr or Br2 across an alkyne. You'll see something, a new term that we're going to allude to called tautomerization. And what I'm going to do is I'm going to start this reaction in a very typical way that we're used to, an acid, like HCl. So let me begin with our alkyne. And we have an acid like, I don't know, HCl, H2SO4, all the typical acids that we would consider. And we're going to do a pi-base mechanism. The pi bond acts as the nucleophile / base. Base grabs the proton, kicks out the leaving group. You know, so far so good. We're going to form the hydrogen on one side and the carbocation on the other. Now, here's the difference. I showed you what happens when you don't use a solvent with HCl. Okay, that was typical. Now I'm going to introduce a solvent, a protic solvent, namely in this case, water. So what's going to happen is you're going to do your SN1. So far so good. So far, I should amend this. This should be pi-base / SN1, then acid-base chemistry. So my water comes on. I've got the water now attached. And you'd think, oh, okay, just have to deprotonate and we're done. But there's something more we got to discuss. There is no second reaction, right? In the bromine Br2 across an alkyne, it would just happen twice. Same mechanism happens twice. And just if I just had HCl, no water, I would have HCl adding twice. The problem here is that we end up, after this proton is removed, a proton could be removed by more water, the floating around Cl-, anything. Either way, I don't really mind which way you do it. But we end up with this product here. And it may not look strange to you, but this is a new functional group. This is called an enol. And I want you to learn it as a new functional group. When the alcohol is a vinyl, it's an enol. Okay, well, I'm going to come back to this. Whenever you spot an enol, I want you to think, ooh, whoa, elephant in the room, there's an enol. Is that okay? I want it to emote some sort of strange feeling like, ooh, I might not be done. I don't typically end in enols. What's going on here? So I need this to be a flashing signal for you. And so in order for that to happen, you need to recognize them. An alcohol at a vinyl position. Okay, that's your new thing to be on the lookout for. Red alert, there's an enol. Why is this interesting? Why is this something that we have to be on the alert for? Well, the most acidic proton of an enol is the hydrogen on the oxygen. I think that you guys would agree to that. You'd say, yeah, that hydrogen is on an oxygen, so if you take it off, the oxygen's negatively charged. Okay. If I were to look over on the right, this ketone, now you see these equilibrium arrows, and you're like, what is going on? Well, if I look to the right, I see a ketone. And the most acidic proton on a ketone is actually at the alpha position, meaning the position right next door, the carbon right next door to a carbonyl. Alpha, allylic, right? It's in an allylic type position. When it's a carbonyl, we specifically call it an alpha position. These are the most acidic protons, not the ones way over. Why? Because if you removed them, the negative charge would have resonance with the carbonyl. Okay, this isn't anything new. Why is she bringing this term in now? If I looked at the pKa for this proton, it would be about 19. If I looked at the pKa for this enol, it would be about, I don't know, -5, -7, somewhere around there. Now we know that when there's a large difference in pKa units between two species, if they're in equilibrium, they're going to shift towards the weaker acid. So notice the arrows here. The arrows are favoring the ketone. This is why the term keto-enol tautomerization has become a thing. Tautomerization is a very specific acid-base equilibrium. So it's just a fancy name for the equilibrium between an enol and its carbonyl form. Okay, so here's the enol and here's the carbonyl. Now, I can't use the word always, but 90% plus of the time, the ketone or the carbonyl will be favored over the enol. How does this even happen? How does this shift occur? Well, let's look at two different scenarios. If I was under acidic conditions, which in the previous case I was using HCl, okay? So if I have acidic conditions and I have an enol, let's just say I have H plus HCl floating around, okay, just like in the previous case. Well, we know that pi bonds are susceptible to acid, right? And if I have an oxygen is a great donating group. Why? It has those lone pairs, right? So if I do this pi base, if I do this acid base reaction with the pi bond, I want the carbocation to form right at the more substituted, but even better than that, I want it to form at the foot of the oxygen. Okay, so that the lone pair by resonance can stabilize. I mean, wow, that's powerful. That's not induction, that's resonance stabilization. And that's how I get to the carbonyl version. I went from the enol under acidic conditions to the carbonyl. Because let's face it, of these two resonance structures, the carbonyl is better. It's not charged and all of the atoms have an octet. Oops, and I'm forgetting my protonated oxygen. That's fine. We're under acidic conditions. Of these two, the acid-base equilibrium lies far to the right, and then you work it up. We're under acidic conditions, so I would neutralize during the workup to remove that extra proton. All right, well, what if I was under basic conditions? Would things be any different? Not really. Start with the enol. If I was under basic conditions, like, I don't know, say OH minus NaOH, guess what would happen? Well, the most acidic proton, as we mentioned, pKa is very low. That base is going to grab the proton, giving the electrons to the oxygen. Okay, how do I know this equilibrium lies far to the right? Well, I just told you the pKa over here is like, I don't know, -5, -7, and the conjugate acid on the other side would be water, which is 15.7. We know that the equilibrium favors the weaker acid, so it lies way far to the right. And we're done, right? All we have to do is work this thing up under acidic conditions. You're going to say, what? Well, if I added some acidic conditions, we already know that the pi bond is susceptible to acid. And so what this does is the negative charge comes down and the pi bond grabs the proton. And again, you end up at the same place, the carbonyl. So no matter what you do, the enol is unstable. Okay, starting with an enol, if you're under basic conditions, boom, tautomerizes to the carbonyl. Under acidic conditions, boom, tautomerizes to the carbonyl. Either way you look at it, acidic or basic, it's not going to stay as the enol. It's unstable, highly reactive. Let's go back to this. After the first hydrogen, right? So if we've added a hydrogen, and then we add the oxygen, after the first addition of the oxygen and the hydrogen, I can't do this reaction again. Why? Because it's unstable. After the first HOH addition across the pi system, I immediately form an enol, and under these acidic conditions, it tautomerizes, and that's just a fancy word for a specific acid-base reaction favoring, look at the carbon here, the carbon bearing the oxygen is the one that tautomerizes to the carbonyl. That is hydration of an alkyne. It starts off the same, but instead of doing it a second time, you have to recognize the enol and just tautomerize it. Here's some practice for you to try yourself. One product is what you get for the first one, and two products are what you get for the second one. I'm just using H2SO4 as the acid in these cases. Another favorite, oxymercuration. This time I'm going to use an asymmetric alkyne. Now, I'm just using a slight variant on the mercury reagent, but ultimately it's the same thing. The sulfate is -2, the mercury is +2, just like it was in the other case, but instead of two leaving groups, I have one ion that is dissociative. So let's just consider mercury. Okay, the mercury is a 2+, and remember, it has a lone pair, just like it did before. It's just the same as we did before. We're going to do a syn3 mechanism. Pi bond makes the first bond, and the lone pair makes the second, all in one fell swoop. We form a very unstable intermediate. Now, just like before, we have a three-membered bridge, mercury intermediate. It's charged. It is charged. It is going to bond elongate, and it's going to direct the solvent, in this case water, to attack the more electrophilic carbon. You can see now why I gave the warning at the beginning of this chapter. If you don't know the alkene chemistry, all of this is news to you, right? I don't want this to be a new thing. We've already seen this syn3 reaction before. I did forget to write SN1. It's followed by an SN1-like mechanism. The water is going to be directed. It's the weak nucleophile. But since the mercury bridge is still attached, the water is going to come in from the opposite side and open the three-membered ring, relieving it of the strain. And we end up here. The mercury got its electrons back, so now it's just +1. Okay, well, after a little bit of acid-base chemistry, right? Maybe the water grabs the extra proton. Where are we? It's upside down from how we saw it before, but really you should not care about its geometry. you see that guy right there? There's your enol. This is why we only can do it one time. Enol. So immediately, these things are not stable. It's going to, under these conditions, favor, and look, I'm doing it under acidic conditions. So I'm definitely going to tautomerize this. Already wrote the mechanism for you out before. We are now here. Okay, but we're under acidic conditions and we still have to contend with this mercury. Well, the mercury wants to go back to being 2+, so it's got to give up its electrons. And the way that this works is that under these acidic conditions, H2SO4, which is just H+, the mercury leaves and gives the electrons to the carbon system, and these pi electrons grab the proton from the acid. This brings me here. Which is an enol again, which doesn't last. It tautomerizes to, let me count my carbons, 1, 2, 3, 1, 2, 3. The enol alcohol was on carbon 2, so after tautomerization, you end up with this product, which is a carbonyl. So terminal alkynes are less reactive towards acid catalyzed hydration. So using H2SO4 and water just alone sometimes isn't good enough. So that's why we turn to oxymercuration in these cases. Okay, so again, you can think of this as your SYN3, SN1, followed by acid-base tautomerization. It's not like in the other cases where you just did the mechanism 2 times. You do the mechanism once, you end with an enol, you tautomerize, which is more acid-base chemistry. Here's some practice for you. Here's where you can generate the product in question 1, and in question 2, it's more of a retrosynthetic analysis. It's trying to go backwards, having you see the carbonyl and determine which enol it most likely came from. Just like alkenes, we could also do hydroboration. Now, hydroboration will get us somewhere a little different, and we can compare and contrast in a second. But hydroboration, I'm going to use an asymmetric alkyne again. Carbon 1, 2, 3. And the ones that I prefer to use, as I mentioned in the previous chapter, is I like to use the boranes that have a lot of steric bulk to them. Why? Well, they work a little bit better selectively to give you regioselectivity when you're doing this reaction mechanism, because alkynes are very linear. So there's like 180 degrees of space for these molecules to come in. So there's not as much steric hindrance, right? If I just have this little methyl, carbon 1, you know, what's going to govern having the boron versus the hydrogen go on one side versus the other? Because there's so much linear space. So in these cases, you tend to see the common reagents like this dicyamylborane, or 9-BBN as we call it, which is a bicyclic system. Lots of, I mean, look how sterically hindering these guys are. That way, you have to use them stoichiometrically. So you have to use them in a 1-to-1 ratio because there's only one hydrogen to deliver. However, the boron has all that steric bulk. You really do get some good selectivity when you're using these types of reagents on an alkyne because of all that room. So I'll use one of those, but I'm just going to use, I don't want to draw those out, so I'm just going to use R2 to represent those big bulky groups. So I have 2 choices, right? I could put the boron on this side with the big groups, or I could put the boron on the other side with the big groups. And I'd rather put the boron with the two big honkin' R groups over on the right because that is on the side with the hydrogen, so there'll be less steric hindrance. So I'm going to orient this sp2 boron in a fashion that delivers Syn4 across carbons 2 and 3. Let's push our electrons. So now I have carbon 2 and 3, carbon 1, which is my methyl, carbon 2 and 3, and Syn. So I got hydrogen at 2 and the boron with those two R groups at 3. Now, this is a perfectly fine, neutral, stable molecule. I've actually made these, and you can choose to stay here and store them and do other stuff with them, or you can move forward. If I didn't give you step 1B, this would be your final answer. Done. Okay? It's not an enol, it's a vinyl borane. Perfectly fine. However, in this case, I am giving you a second step. Right? And the first step was Syn4. The next step is just like the alkene system. I'm not going to put you through it again. This is that 1-page long, oh my gosh, it's so long mechanism where we oxidize off the boron, but we keep the stereoselectivity of the borane face. So, ooh, magic happens, and the boron gets exchanged for an OH at the end of the day. You can review that mechanism if you forget and want to convince yourself that it's not fairy dust and magic. Okay, but once we do that, once that happens, can we do a second hydroboration? Look at what happens after that exchange. We have an enol, and we're under basic conditions, and it doesn't really matter. It seems like enols just don't stay put anyway. So what's acid-base tautomerization is going to occur. Carbon 1, 2, 3. This time, the oxygen's on carbon 3. It happened to be on the less substituted side. Carbon 1, carbon 2, carbon 3. I made an aldehyde in this case. So when I had this alkyne from the previous slide, and I reacted it with mercury sulfate and water and H2SO4, some acid, 1, 2, 3. I put the enol at the more substituted position, 1, 2, 3, and that tautomerized into the ketone. So starting from the same starting material, doing oxymercuration gave me the ketone, and like in this slide, the hydroboration, because it operates under a different mechanism, right? The mechanism is Syn4, so it's governed by steric hindrance. And so this Syn-concerted mechanism led me to putting the oxygen at the less substituted position after tautomerization, leading to an aldehyde. While in the previous case, I wasn't doing Syn4, I was doing Syn3, then followed by an SN1. It was all governed by putting the oxygen at the more substituted position because of a more positively stable carbon. Completely different mechanism, thus leading me to a ketone. That's interesting. So this is kind of cool because we've got two different methods of turning an alkyne into a carbonyl, and if I have an asymmetric alkyne, I may be able to govern which side gets the oxygen. Here's some practice for you to try.